Okay, let's see some examples of Turing machines. And the first example is a Turing machine that accepts the strings W, $W. So this language is not context-free. It's of course not regular, which is easy to prove. The fact that it's not context-free, requires using some tools that we have not seen yet, and we will not see in this semester. So you would have to take it on faith. So it's not context-free, and now we are going to show that nevertheless it's easy to build a Turing machine for it. Here, let's assume that the alphabet is A and B. So, for example, the word in the language would be ABA, $ABA. Okay? And then, of course, blank, 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 blank. Okay, so initially the reading head is on the first A, and the start state is this one, Q0, and when it sees an A, it converts it to an X and moves to the right. So this now becomes XBA, $ABA, and the head is here. Now, as long we're in this state, as long as the Turing machine sees B as an A, it moves to the right. So the head is going to move to the right all the way to the $. Once it gets to the $, it's going to take the transition on the $. That tells it just go to the right. Okay, and the idea now is that the Turing machine is just going to turn the first A it encounters into an X, right? So essentially it's going to do this elimination, right? It's going to find the letter on the left, run all the way to the right, copy, delete it, and repeatedly do it, and make sure that the deletions match, and then when it's done, it will just make sure that everything is deleted correctly. Okay, so now we have to delete an A. So first, as long as we see, we're in this state Q2, as long as we see the letter X, we just go to the right. X is this already deleted letter, but we don't have any X, we have an A. So we go down to Q4, replacing the A by an X, right? So the string is becoming now XBA, $XBA, and the head is on the $. We are in this state, Q4. With the $, we just move to the left, so we are now here. And now we're in this state. This state tells us as long as we see an A and a B, just move left. So the head is just going to move left until it gets to the X. When it gets to the X, it's going to take this transition. This transition tell it, oh, well, just take the X, just move the head to the right, and go back to the start state. So after this is done, we are here in the B. And now we have to do the same thing with the B. And if you notice, our Turing machine looks like has a symmetry in the middle because the bottom part does the same thing for B letters, right? So indeed, as long now that it got to B, it's going to go on the right transition, replace it by an X. So this is going to be XXA. As before, it's going to run all the way to the $, and then once it's in the $, it's going to be XBA, right? So let's do it. It replaced the B by an X. Then as long as it's A and B, it goes to the right. It goes to the right when it's in the $. So now we are in the first X. Now that it sees an X, it goes to the right. So it would arrive to the B, and then the transition here says replace the B by an X. So this is now becoming XXA, $XXA. And the head is moving to the left, so it's here. And now you do the regular backtracking, right? As long as there is an X, you go to the left. So we go till the $. Now that we go to the $, we go to the left, right? So we are here. And now as long as we see A and B, we go to the left, so we get, oops. So we go to the first X. Once we encounter the X, we move to the right and we're back in the start position. So the machine's snapshot is now this one. Okay, and now we do another run, deleting the A, right? We delete the A and we delete the other one and so forth. And now we get XXX dollar XXX. Seems like a really highly inappropriated rated movie. And we reach the dollar, and as before, we are in the start state. Now, if the start state sees a dollar, it goes down, right? And all it does when it sees a dollar, it replaces it by an X, because why not? So now the string is just going to be XXXX, XXX, X, even worse rated movie. And now it just keep going to the right until it hits a blank. When it hits a blank, it just replaces it by a blank, move that to the right and accepts. So it accepts this string. Okay, the interesting case, of course, is what happens if I give it a string that it shouldn't accept, right? Think about the case, for example, where the string is, well, let's take a minimal bad example, or close to minimal, $A$B, right? So what happened in this case is that, the same algorithm would follow. We will go in the start state, replace it by an X, run to the right, go on the dollar, get to this state, and now, so the input is now $X$B, and the read head is in this location, and we are currently in the state Q2, and now there is no transition for B, so the machine would just crash, right? Now, of course, we could have been nicer about it and create a reject state and move all the missing missing transition to this reject state. But this drawing is just to keep the minimal number of states available. But, of course, that would be a better thing than just crashing in this case. So this is the Turing machine for accepting $W$W.